Alright, we've been studying linear inequalities. It's very similar to solving equations, only instead of having one solution like we do with equations or equalities, with inequalities we have a whole range of solutions. For example, here, as long as x is smaller than -1 or -1, then we can count on values for the blue line, represented by 2x plus 9, will always be less in value than the red line, represented by 6 minus x. So, moving on, we should remember to use our technology. I've created a program for you guys to use if you want to, but it would be a wrong thing to do all of this work from the previous slide, to do all of this work and end up being wrong in your thinking half the time. So the technology exists here. You can identify one line being red and the other line being blue, and you can see the solution is actually already prescribed by the program. So you'll know the red line is above the blue line, then this is going to be the part of the greater than side, and this is going to be part of the less than side. So I encourage you to use that prior to Fridays, or prior to the next exam. Alright, so just quickly, this is to show or to demonstrate that the work that I'm asking you to do, a lot of it should be mental, and so in practice, if you're taking an ACT test, the following is something that you can visualize. You should be able to see a steep line crossing below the y-axis, as represented by -1 minus 8x if I distribute the negative. Blue line is a decreasing slope but not quite as fast, crossing above the x-axis. So I can perceive the intersection of these two lines as a value of x that's less than 0 or negative. So then when I do the work, algebraically, I solve the equation, I don't worry about the inequality, and I end up with x equals -1, which is where I visualize. And now that I have this graph in my head, I can see the steeper line should be above the blue line. So I'm looking for this red stuff above the blue stuff, which happens when we are less than -1. Blue below red. So that means my solution set is I'm going to go from -infinity to -1 again. Same solution set as before, different system. Anyway, we can apply what we've learned with absolute value equations and inequalities to now solve absolute value inequalities. We'll put the two ideas together. So in the previous unit, we learned how to graph 2x minus 6 absolute value, and we ended up with a line whose equation is going to be y equals 2x minus 6. Another one will be negative 2x plus 6, the negative slope and the positive y-intercept. Here we have the line y equals 8, and we can see intersections probably here at -1, probably over here at 7 or something like that. We'll see. So we can algebraically break up the absolute value into two parts. One of them where we have the what's inside the absolute value, just leave it alone, solve the equation, we get x equals 7. And the other where we take the opposite, but take the opposite of the 2, take the opposite of the -6, and we solve the equation that way, and we get x equals -1. So we can see those numbers matching what we found on our graph. Furthermore, we can see that since the inequality is what we're looking for, we want the absolute value stuff to be lower than 8. So we're going to take all the stuff that's below, and that happens whenever x is between -1 and 7. So that's my solution set. Don't forget, I should have done this in the first place, to label the rays, because then you can see this equation is 2x minus 6 and y equals 8. Here's 2x minus 6 and 8. That's where the 7 comes from, right here. And here we have the negative 2x plus 6. Here's negative 2x plus 6 equals 8. So these should match up as well. And just to verify, when x equals 0, which is one of the numbers between -1 and 7, my inequality is in fact true. So now, sometimes you can see inequalities written in a variety of different ways. So before graphing, we might need to do some modifications to numbers from 63 to 66. For example, in number 66, we see 3/4 times the quantity x minus 1. We can simply write it this way. And then we can take out the 3/4, so we can see the slope of the rays are going to be plus or minus 3/4, and the x-intercept is going to be a 1, 0. So we can graph the line with a slope of 3/4 by going over 4 up 3, and back 4 up 3, and we get the negative 3/4 slope in there. So this is not the complete part of the problem, but in terms of graphing, we make some modifications before we graph, so then we can see our rays better. and our transformations as well. Sometimes we might be faced with two inequalities, which poses an interesting question because this could be positive or negative and this could be positive or negative, but there could be times when one should be positive and the other should be negative. It gets a little confusing. Thankfully we have a graphical approach to help clean things up a little bit for us. So here we observe that the y equals 2 times the absolute value of x is going to produce an absolute value graph where the slope is 2, so over 1 up 2, and negative 2. So y equals 2x this way, and y equals negative 2x that way. On the other side, we have y equals the absolute value of x minus 5. That's going to have slopes of plus or minus 1 shifted to the right 5. So we can see that we will find a y-intercept of 5, x-intercept of 5, and slopes are 1 and negative 1 accordingly. So I make a point of labeling each of the rays. Remember, you can use the slope, positive or negative, and you'll know to be 2 based on the equation. And then we've got the y-intercepts, which here if we extend it should be negative, and here if we look at this y-intercept it should be here at 0, 5, which it is. So that's just verifying that the rays match what you see on the graph. Now what we're able to do is break this into 4 different equations. To see how they're broken up, the first thing we'll do is change this absolute value into one where we leave it alone, and the other where we take the opposite of everything inside. Now we have 2 more absolute value equations that have to be broken up. So one, leave it alone, and the other, take the opposite of what's inside. One where we leave it alone, and the other where we take the opposite of what's inside. This creates 4 different equations, but when I look at the graph I can see that there are only 2 solutions. There's an intersection here when x is a negative number, and here when x seems to be between 1 and 2. So these are the only 2 solutions, yet I have 4 equations. Rather than solving all 4 of these equations, I can refer to the graph to see where these intersections occur and assign their rays to each other. Here negative x plus 5 should intersect with negative 2x to produce this solution. That is negative x plus 5 intersecting with 2x. And here we see, there's negative 2x. There it is. And then here we see positive 2x intersecting with negative x plus 5. That will show up right here. So the other 2 are lies. We don't even need to bother solving them. In fact, if you don't have the time, don't write them. Just write the 2 equations that you'll have to solve. If time permits, show the other equations, show their lies, show that why they are lies. But the rest, to solve these, to see what they're equal to, and it shows 1 2/3 and negative 5, which is consistent with my graph. So I know I have the right values, and then I want the absolute value, the blue absolute value, the red absolute value has to be below the blue. In other words, the blue has to be above the red. The blue is above the red here, the red is below the blue here, so this is the solution set. And that means any number from negative 5 to 1 2/3, not including those because it's not less than or greater than or equal to. Just to verify, 0 is a number between negative 5 and 1 2/3, which does create a true inequality when substituted. Don't forget, look through the technology to see that the intersections match where they're supposed to, and you can also see that the blue curve again is below the red curve in the appropriate places. So use the technology, that's what it's there for. Thanks for watching.